Generator connection accessories. Forced air cooling. Introduction. Forced air cooled. Fact. Isolated phase bus bar. Isolated phase bus with rated current above 25 kA tend to be forced air cooled to reduce the overall size of the bus enclosure and conductor. This requirement is necessitated to meet constraints of space near the generator and indoor area of the station. Ease of manufacturing, transport, and installation. Reduce the initial cost of the installed equipment. A forced air-cooled bus also has a natural air-cooled rating. The ratio of natural to forced air-cooled rating depends upon the quantum of heat evacuated by the cooling equipment. There is no specific value to the ratio. The sizing can be carried out for the following constraints if specified. Forced air-cooled rating of the bus. Natural air-cooled rating of the bus, should the forced air cooling equipment fail to operate. Ability to meet the specified temperature rise constraint at rated current for the failure of the cooling equipment for a specified duration of time. Evidently, the time duration has a limiting value depending upon the time constant of the isolated phase bus. A unit that requires a forced air-cooled isolated phase bus will be large enough to warrant a delta connection at the banks of 3 single-phase generator transformers. These connections are confined to an outdoor area that does not have any space constraints. The current in the delta connections will be root 3 times less than in the main connections. It is, therefore, the practice to size the delta connections for natural air-cooled rating. The current rating of delta connection of an isolated phase bus is likely to be less than 25 kA in most of the units. Should it be exceeded for an unusually large rating of the unit with rated line current above 43.3 kA, it can still be designed to operate under natural cooling since there are no space constraints in the outdoor area where these are installed. The tap-off connections are always designed for naturally air-cooled criteria. 2 types of forced air cooling systems are adopted in an isolated phase bus. Open loop, closed loop and convertible closed loop. Open loop system. In the open loop system, the ambient air is filtered, dehumidified, and fed to a blower. The blower is connected to an inlet manifold and the air is distributed to each of the phases of the isolated phase bus through individual dampers. The inlet to the isolated phase bus is normally indoors near the generator. The air travels through the annular space between the conductor and enclosure of the bus. It is discharged to the atmosphere at the far end of the isolated phase bus, near the generator transformer. The airflow rate can be controlled at the inlet of each phase to ensure a uniform temperature at the outlet of each phase. The temperature of the conductor and enclosure will be higher near the outlet. The temperature gradient along the length of the isolated phase bus will not be linear. The cooling will be most efficient at the inlet since the temperature of the air at the inlet will be minimum at ambient, while at the outlet it will be maximum as it absorbs the heat during its travel. The heat generation along the length also will not be uniform since the resistance will increase with the temperature. The velocity of air increases as it travels through the length of the isolated phase bus since the air will expand with the increase in temperature. Open loop systems are uneconomical and are not the preferred means of forced cooling. Closed loop system. In a closed loop system, different airflow pattern and direction of flow can be established. This will depend upon the layout of the isolated phase bus bar. Air can be fed into extreme 2 phases, through a common manifold, near the generator. Air travels to the end near the generator transformer where it is led into the center phase through suitable aluminium ducts. The return air travels through the middle phase and is evacuated through an outlet that is located very close to the inlet manifold. The inlet and the outlet are connected to the forced air cooling equipment. Alternatively, air can be fed in the middle of the extreme phases, forced to travel to both the ends at generator and generator transformer and return through the middle phase. Here also the inlet manifold is located very close to the outlet and connected to the forced air cooling equipment. Keeping the inlet and outlet close to each other reduces the external ducting to the forced air cooling equipment. Controlling dampers are installed at the inlet of each extreme phase to regulate the discharge. It is evident that the discharge and consequently the velocity of air in the center phase will be almost double that of the 2 extreme phases. Smaller duct lengths will result in a lesser heat loss and smaller pressure drops. In the event of a failure of the heat exchanger, provision can be made to convert a closed loop system into an open loop system. This is also referred to as a convertible closed loop system. Figure 8.19 illustrates the enclosure temperature along the length of the isolated phase bus with inlet feed at the extreme phases and outlet from the middle phase. The inlet and outlet are near the generator. The velocity of air in the middle phase will be approximately twice that of the air in the extreme phases. The velocity of air increases with the travel as it expands while absorbing the heat and raising its temperature. The interconnecting air ducts between the phases have earthed deionizing plates to remove any electrical charges from the air. Forced air cooling equipment. Forced air cooling or FAC equipment can be installed for the evacuation of heat from the conductor and enclosure of isolated phase bus connected to large generators. Forced air cooling equipment circulates clean dry air at a designated temperature into the annular space between the conductor and enclosure of the isolated phase busbar system. The blower is designed for the delivery of a specified minimum discharge. The cooling of the conductor and enclosure is affected primarily by convection along the entire route length of the connection. Depending upon the airflow, the equipment can be classified under an open loop or a closed loop system. In the open loop system of forced cooling, the outlet cooling air from the isolated phase bus is discharged into the atmosphere. Consequently, clean inlet air to the cooling system has to be extracted from the atmosphere at a temperature not exceeding the specified air inlet temperature. Since the isolated phase bus will be designed for a maximum ambient temperature for its natural air-cooled rating, air from the surrounding area can be used at the inlet. Most isolated phase bus with forced air cooling use a closed-loop system wherein the air from the IPB outlet is recirculated through a heat exchanger to the inlet of a cooling system. In such a case, an air-to-water heat exchanger is usually incorporated as it is the most compact, efficient, and economical device. The power requirement for the forced cooling system is added to the losses in the isolated phase bus for capitalization. The forced air cooling system comprises the following: a motor-driven centrifugal blower to supply air at a designated discharge and temperature to the inlet of the isolated phase bus to maintain the temperature rise of the enclosure and conductor of the isolated phase bus within the specified limits when operating at rated current. An air-to-water heat exchanger to cool the hot air from the outlet of the isolated phase bus that is fed back into the inlets of the isolated phase bus at the designated temperature. Air ducts and manifolds as required to connect airflows to and from the forced air cooling unit to the isolated phase bus. Deionizing barriers to neutralize the charges when air flows from the enclosure of one phase to another. These are usually installed in turnaround ducts at the generator and generator transformer ends of the isolated phase bus. Air filters and dehumidifiers, if needed, in the loop to maintain the quality of air. Airflow and temperature measurement at designated locations. Baffles and dampers to control and balance the flow of air in the isolated phase bus. Control panel for distribution of power, control, measurement, protection, and monitoring of blower system. Redundancies may be built as required. Many project specifications call for a convertible closed-loop system, incorporating a mechanism that enables a closed-loop system to be converted into an open-loop system in the event of a failure of the air-to-water heat exchanger. During the changeover, the temperature of the conductor and enclosure shall remain within the specified limits for such a contingency. Forced air cooling systems, where installed, can also be used to clear the moisture and dust from inside the isolated phase bus before energizing the same after a period of shutdown. Provision can be made to heat the inlet air to the desired temperature before circulating it inside the isolated phase bus. Those sections of the isolated phase bus that are not included in the forced air cooling circuit can be subjected to hot air blowing from a portable device. Thank you. For a comprehensive understanding of the theory and practices of busbar systems, it is advisable to read the book An Introduction to Busbar Systems, where contents are organized in a sequence for ease of reading and facilitates cross-reference. Please procure a copy of the book with a requisition to Bala at busbarsystems.net.